Go, I am Mr. Bishop, the Bitmoji with the shark costume right here. This is chapter 3, day 6. We're still doing applications of linear programming, and this time we're going to look at problems that involve a minimum or minimizing an objective function. So a couple things for us to recall that we already know. For starters, we already learned about the fundamental theorem of linear programming, which says the maximum value or the minimum value of the objective function is achieved at one of the vertices, or I call them corner points, right? It's achieved at one of the vertices of the feasible set. So that's why we do all that graphing and then shade false. Our feasible set is that open area. And then to find the maximum or the minimum, we don't have to check every single point in the feasible set. All we have to do is check each corner point or each vertice, if you will. And we plug it into the objective function to see which point gives us our maximum or our minimum. So that's what the fundamental theorem of linear programming says. And a quick example that I've shown you before, right? If I get done with my feasible set and it looks like this weird shape like this, all I have to do is check these corner points, plug in the x, y values from those corner points, and figure out which one either gives me my maximum or my minimum, whatever I'm looking for. Okay, so that's just a refresher. We've already talked about those in a previous video. Let's take a look at the day 6 worksheet. I'm going to do one of these problems with you. There's 3 problems total on the worksheet. So I'm going to do number 13 here to start. So this one's about nutrition. It says Mr. Smith decides to feed his pet Doberman Pinscher a combination of 2 dog foods. I'm a pit bull person myself, but Doberman Pinschers are fine also, by the way. So each can of brand A, so that's 1 dog food, contains 3 units of protein, 1 unit of carbs, and 2 units of fat, and costs 80 cents per can. Each can of brand B, so brand B contains 1 unit of protein, 1 unit of carbs, and 6 units of fat, and only costs 50 cents per can. It says Mr. Smith feels that each day his dog should have at least 6 units of protein, 4 units of carbs, and 12 units of fat. So it needs to have at least that much in its diet. How many cans of each dog food should he give to his dog each day to provide the minimum requirements at the least cost? So Mr. Smith's got to feed his dog, make sure his dog's healthy, but he's also on a budget, so he wants to minimize the cost here. Okay, so we've got a blank table in front of us. And you should be able to handle filling this out just from the tables you've seen before. But let's start with, we know we have brand A dog food, so I'm going to put brand A at the top of this row, and brand B at the top of this row. So this first box here is going to stay blank, right? We'll darken that in, we won't need it. And then right underneath that, we'll do protein, and we'll do protein for each brand. So protein goes here. And then we've also got carbs, and we've got fat. Okay, setup looks good so far. And then the objective function is going to go in the last row. And our objective is to minimize the cost. So we'll talk about the cost for each can in the last row there. And then over here at the top of this column, those will be our minimum requirements for our diet. So I'm just going to put the diet requirement, and then we'll map out each one: protein, carbs, and fat. And again, we don't need anything in this box, so I'm going to go ahead and just darken that in for now. So we've got the labels all set up. That's the difficult part, really. Now we just need to put the numbers from the problem here down into our table. So brand A for protein, it said 3 units, 1 unit of carbs for brand A, and 2 units of fat for brand A. And the cost of brand A was 80 cents per can. So I'm going to put 80 cents there. And then continuing down the line here, we got brand B, which only had 1 unit of protein. It had 1 unit of carbs and 6 units of fat. And brand B was a little cheaper. It only costs 50 cents per can. Last but not least, we got the diet requirement for the dog. So it says the dog should have at least 6 units of protein. There we go, 6 for protein, 4 units of carbs, and 12 units of fat. There we go. The table is complete. Now we just have to answer the question, how many cans of each type should he give his dog so that he can be at a minimum cost? So to do that, we're going to move forward with graphing and shading like we know how to do. So why don't we let X be the number of cans for brand A, and Y will be the number of cans for brand B. So basically we just put X's down here through brand A, and Y's down here through brand B. And our objective, if I could just talk about the cost, right? We want to minimize the cost function. So I'm just going to say C equals, and I know it's 80 cents for every brand A can plus 50 cents for every brand B can. So we want to minimize that objective function. Okay, so let's get to our constraints, right? We have to put these into some inequalities before we can graph and shade them. So the constraint for protein looks like we have 3x plus 1y and then a 6 on the other side. So the big question right now, the big decision, what are you going to put in there in terms of an inequality? Is it greater than or equal to or less than or equal to? Well, notice the dog should have at least, it says at least 6 units protein, 4 units carbs, and 12 units of fat. So if it says at least, that tells me I need to be greater than or equal to. So that's greater than or equal to, meaning no matter how much brand A and brand B you buy, you better have at least 6 units for the protein. So I'm going to go ahead and make that a little nicer there. That should be greater than or equal to. Again, you wouldn't want to have a less than sign there because these are the minimum diet requirements for the dog, right? You don't want to starve the dog, so make sure it gets at least 6 between brand A and brand B cans. All right, and then our constraint for carbs. Reading the table from left to right there, we have 1x plus 1y, and then a 4 on the other side. Again, we need at least 4 units of carbs between our 2 dog food brands, so make sure whatever you have for x plus y is greater than or equal to 4. And then for fats, we have 2x plus 6y, and then a 12. Again, you've got to have at least 12 units of fat in the dog's diet, so make sure this is a greater than or equal to sign. And last but not least, since we're dealing with a realistic problem and we can't feed the dog negative cans of dog food, we know X and Y both have to be at least 0. Even if you give the dog all X, right, brand A cans, that means you give 0 for Y. So make sure you have those 2 constraints at the very end as well. All right, so we've got our constraints. Let's move forward with graphing and shading here by getting Y isolated on one side. So that's pretty easy for the first 2. For protein, we just need to subtract 3x on both sides. And I'm going to do this one in purple. We get Y is greater than or equal to negative 3x plus 6. All right, so that one is ready to graph. Let's go ahead and solve the next one. Let's get Y by itself. Only one move. Just subtract x on both sides. And I'm going to do this one in green. We have Y is greater than or equal to negative x plus 4. And then the third one there, this is going to require 2 moves, right? So let's start by subtracting 2x on both sides. and we get 6y is greater than or equal to negative 2x plus 12. And then we want to isolate y, get it by itself, so we have to divide everything through there by 6. So divide everything through by 6, and we get y is greater than or equal to negative 1/3 x, if we simplify, plus 2. Perfect, so we're ready to get to the graph. I'm going to start with the purple line here. Looks like we have a y-intercept of 6, so I'm going to go ahead and put a dot at 6. And then our slope would be negative 3, so down 3 over 1. So I'm going to go down 3 over 1, put a dot. We'll do that all the way across the first quadrant here. Down 3 over 1, and then make my line. And I have a straight line tool on my iPad, but if you have a credit card or a ruler or something with a straight edge, that will help you make these lines more precise. All right, and for the green line there, looks like I start at a y-intercept of 4, so I'm going to put a green dot at 4, and then it's just negative 1 for the slope, so you know it's down 1, right 1, all the way through. And then I can see clearly that they intersect right there. Down 1, right 1, across the first quadrant, and let's make the line. And last but not least, I have my blue line here. It starts at 2 for the y-intercept. I'm going to put a blue dot at 2. And then it's down 1 over 3. So down 1, right 3, and I can see it intersects the green line right there. Down 1 over 3, and go ahead and make my line. All right, and we're going to start shading these. Remember, our goal is always just to shade false, so that when we get done, the open area is our feasible set. I'm going to knock out these two guys first, like I always do. I'm going to do those in gold. So x greater than or equal to 0, y greater than or equal to 0. I'm going to knock those out and shade false. So I'm going to put a line across right here at y equals 0. And then since I'm shading false, I'm going to shade everything below that line. And then the same thing, I'm going to put a vertical line here at x equals 0. And then since I'm shading false, I'm going to shade everything to the left of that. All the numbers less than 0, right? I'm shading false. So anytime we're doing a real life scenario, those two constraints will always be there. I don't know why I always like to do it in gold on my iPad, but I want to knock those out first. Okay, and for all three of our diagonal lines here, our other three constraints, it's y is greater than or equal to for every single one. So if I'm thinking about shading, usually I'll say, oh, if this was the roof of a house, these diagonals here, y greater than means I'd shade above, right? But since I'm shading false, I'm going to look to shade below each one of these lines. So y is greater than for purple, I'm going to shade below the purple line. So here we go. And again, I don't write that fast, right? I try to draw these out beforehand and just play it back so it looks decent, right? I'm not just like a crazy fast person that shades these things. Again, for the green line, I'm shading false, so I'm going to shade below the green line. There we go, in green. And one more time for the blue line, since it's y is greater than, and I'm doing false, right? I'm going to do the opposite of greater than the roof, which means I'm going to shade below the roof here. Excellent. I really like this. I'm getting my I'm channeling my Bob Ross again. Here we go. We've got our feasible set now. We're done graphing and shading, so I'm going to go ahead and highlight in pink here, right? We got our feasible set. It's this open region. In fact, it would continue out forever, right? That arrow, this line would continue out forever. That vertical line would continue out forever. But don't worry, we don't have to check infinity points. We just have to check the corner points. Where do our lines have intersections here? So we just need to identify the corner points or the vertices. So if I can point them out one by one, it looks like we've got one right there, right, where the purple and gold lines cross, and that is at 0, 6. We got another one right there where the purple and green lines intersect, and that is at 1, 3, it looks like. Right here where green and blue intersect, that looks like 3, 1. Last but not least, where blue and gold intersect, and that looks like 6, 0. So 4 clear corner points that we can see here. Again, there's not any more going this way. That line just goes off for infinity. Our intersection points, our vertices, are these 4. Okay, now we need to plug each one into our objective function and see which one gives us a minimum cost. I've kind of run out of room here, so I'm going to make a little bit. There we go. That'll work for me. So let's take each corner point and plug it into our objective function. So our cost function here was 80 cents for each x plus 50 cents for each y. So you should have enough room on your worksheet for this table. Obviously, I just ran out of room in this picture, so I added a new slide. So let's go ahead and give our corner points over here. We got 0, 6, 1, 3, 3, 1, and 6, 0. Those are our 4 corner points. And let's plug each one in. So we have xy coordinates to plug into our xy equation here. So the first point, 80 cents for each x plus 50 cents for each y. 0 for x you plug in, 6 for y you plug in, gives us a cost of $3. Right? Because 50 cents times 6, half of 6 is 3. All right, let's see if that one ends up being the cheapest. The next point is 1, 3. So I'm going to take my cost function here, 80 cents for each x plus 50 cents for each y. I always start out leaving them blank with parentheses. Then I'm going to plug in the 1 for my x, the 3 for my y. Let's see, that's 80 cents plus $1.50, which gives us $2.30. So right now that's the winner. That's the cheapest combination so far. All right, next point is 3, 1. So I'm going to plug it into the objective function for x and y. So 3 for x and 1 for y. Let's see, 3 times 8, that's 240 plus 50 cents. That gives us $2.90. So that's not the winner. So far the winner is still $2.30. We got one more point though. I don't think it's going to be the best because X is the more expensive brand. That's brand A and it has 6 cans of it. So you plug in a 6 for X, a 0 for Y, and you get $4.80. That is the worst one for cost. So our winner is $2.30. That's the cheapest. And let's go ahead and summarize that, because we need to answer the actual question that was asked in this problem all along, which was how many cans of each dog food should he give his dog each day to get the minimum cost, right? So the answer is you get a minimum cost of $2.30 when you give the dog 1 can of brand A and 3 cans of brand B. There you have it. All right, that's how you solve a minimum problem from start to finish in an actual real world scenario. You graph, you shade, you check the corner points, see which one gives you a minimum. I'm Mr. Bishop, the guy in the shark costume, saying that's all for this video. Thanks for watching.